Okay, welcome Alexia and Erez and Fanny and Susanna and Alexis, Stephanie, Max, Adam, Antonio, Diego, and Rigny. Let's get right to the quiz. So I'm going to share my desktop. And let's take a look at the quiz. So what we've got is set up the integral that gives one petal of r equals the cosine of 3 theta. So we had a formula for the area of the of a region, and that was 1/2 the integral of r squared dr, or d theta, sorry. And we need to find out what a and b are. So how do we find out what a and b are for the one petal?
Where theta equals 0.
Yeah, so we want theta to be equal to 0, not theta equals 0, but
Well, the whole thing, like cosine 3 theta equals
right, and that's
0.
r. So it's where r equals 0.
Yeah.
Yeah, because where r equals 0, it's the origin, and that's where the petals meet.
Didn't know how to explain it.
Yeah, it's r. R is a lot easier, isn't it? Okay, so what we do is we just set, and I'm going to call theta t just to make it easier to type. So we're going to have 0 is equal to cosine of 3 theta, call it t. And then you got to remember, when is the cosine of something 0? And that's at odd multiples of pi over 2. Or in other words, 3t is equal to, and now an odd number is 2k plus 1 pi over 2. Any questions so far? Okay, so if you kind of list them, if k is 0, then we have 3t is equal to pi over 2. And if k is 1, that's the next one, then we have that 3t is equal to, well, k is 1, that gives you 2 times 1 plus 1 is 3 pi over 2. Okay, now what we can do is divide by 3. So we can say that t is equal to pi over 6, and t is equal to pi over 2. So there's our a and there's our b. So let's call that equal a. The other one's equal b. Any questions so far? All right, so now we just set up the formula. And I think it's too messy to kind of type it out. So I think I'm going to use a equation. And cosine 3t. So we have the area equals the integral from pi over 3. Let's go find pi over 3 to pi over 2. And usually you throw the 1/2 outside. And then you square r, so that's cosine squared of 3 theta d theta. And that's it, it's set up. Okay, so not too much to do. The hardest part again is finding a and b, but that wasn't too bad. Question 2, find the distance between these 2 points. It's kind of an all or nothing question. Either you remember the distance formula or you don't. Could you have used negative pi over 6? So had you let k, yeah, so you can choose the sequencing of the k's. So had you let k equal -1, let's take a look to see if that would work. Then you get -2 plus 1, which is -1 pi over 2, and then divide by 3 and get negative pi over 6. So you could use negative pi over 6 to pi over 3. That's fine. So when you say can you use negative pi over 6, only if your next one is pi over 3. So they have to be sequential, if that's what you're asking. Okay, the next one is find the distance between these 2 points. So this is all or nothing. Either you remember the distance formula or you don't. And just to make it easier to type, I'm just going to add QRT because the distance formula has a square root. And then what we do is we just subtract 4 minus negative 2 is 6. And that is 36 because we square the difference. And then plus, then we take 3 minus 1 is 2. 2 squared is 4. Plus, then we take negative 1 minus 2 is negative 3. Negative 3 squared is 9. Looks like that. And that's fine. That's all done. Okay, if you want to add them because you just like feel like it, you can, but you don't need to. Any questions on the second question? Okay, although there were 4 questions, they're pretty quick, right? That took a few seconds to do. Okay, question 3 is write the equation of the sphere of radius 4 with center 2, 6, negative 1. So remember, if the radius is 4, then the right-hand side needs to be what? Oh, I missed. So was the last one 1 squared? Let's see. Negative 1 minus 2 is negative 3. And it's negative 3 squared, which is 9. Does that make sense? Okay. Now I'll tell you, I'll let you know something. And when you get older, arithmetic doesn't get better. So it's the one thing you don't get better at in math is arithmetic. So live with it the rest of your life. You know, I make mistakes too. It happens. The key is if you show your work, of course, then I can give you credit. So if all you did is give me an answer with a decimal, that's not so good. But at least if you expressed it like I did, something like that, then I can kind of see that you understood most of it. So that's the lesson on showing work. Okay, we want the equation of a sphere of radius 4 with center 2, 6, negative 1. So again, it's kind of all or nothing. Either you remember spheres or don't. Remember that if the center is the origin, it was x squared plus y squared plus z squared equals the square of the radius. But the center is not the origin, it's 2, 6, negative 1. So what do I have to do to make the center happen?
X minus a squared
Yeah.
plus 6. I mean, y
Exactly.
minus.
I'll just put it easily. You have to subtract each of the components. So
and then the radius is 4 squared. And you make it equal to that.
So it's going to be x minus 2, exactly, squared plus y minus 6 squared plus, and now it's going to be z minus negative 1. I'm going to write a z plus 1 squared is equal to what? $16, exactly. So do you agree these are kind of all or nothing? There's not much to do. There's no calculus here. Okay. Only the first one had some calculus, but okay. So then let's say V is negative 231 and W is 4, negative 1, 5. We want to find the magnitude of V, and we need to find V minus 2W. So the magnitude of V, we have a formula for that. So the formula for the magnitude is the square root of the sum of the squares. I'll use SQRT. And then negative 2 squared is 4. Plus 3 squared is 9. Plus 1 squared is 1. Okay, and if you feel like it, because I got some time, that's equal to square root of 14. Definitely not required to do the final step there. It is hard to resist. Any questions on part A? Okay, part B, we need to find v minus 2w. And the key on this is just component wise. So this was just a quiz on the little tiny facts of vectors. Nothing intense. Every problem is easy if you know what to do. No calculus. So we just take v. So we look at the x component first and we say -2 minus twice 4, or -2 minus 8 is, let me write v minus 2w. And -2 minus 8 is -10. And then I do the same thing with the y coordinate. I take 3 and then minus twice -1. And that's 3 plus 2, and that's 5. Okay, and then I do the same thing with the z coordinate. I just take 1 and then minus twice 5, or 1 minus 10 is -9. And that's all there is to question 4. Any questions on this quiz?
Sort of, Larry. I still am confused about number 1. I feel like in an example in class, it was r equals cosine of 2 theta, and you use the bounds of -pi/4 and +pi/4. So couldn't you use -pi/6 to pi/6 for this situation?
Okay, so let me work this out. So again, we have 3t equals 2k plus 1 pi/2. Okay, so if k is -1, so you wanted to do -pi/, so if k is -1, we get -1 pi/2 is 3t. So divide by 3. It's just simple algebra. I mean,
yeah, I see the process. I just feel like for some reason, I don't know, I'll keep looking at it and maybe I'll ask you later.
Yeah, maybe I'll give you a little warning. Don't memorize one problem and think that all numbers are going to look like that.
Well, no, it's certainly situational. Even looking at it on the graph, it's a pedal. So I feel like it's a 3 pedal, and the first pedal is halfway between the x origin. So the top part is the positive pi/6, and then the bottom is the negative pi/6. And I feel like, wouldn't it only be pi/3 or pi/2, I'm sorry, to make it 0, and then you divide it by 3, which makes it pi/6.
Let's see.
And then,
so we have, if k is, right, so the idea is you do -pi/6, and then if k is 0, then it's pi/6. So it's -pi/6 to pi/6.
okay, well, there it is then.
Yeah, I mean, I didn't do it that way. I did this
Well,
one.
right. I think I may have asked my question poorly. You said the bound would have been to 2, I think 2/3 pi or something like that, and that's why
Okay,
that was
maybe
my question. But
yeah,
it
either
may
I
have been
spoke
in
too quickly
translation,
or you didn't hear me right, one or the other.
or it was my fault. But thank you. That's it.
Yeah, the key is, again, write out the equation so that if there's a little mistake, you get partial credit. Does that make sense?
Yep.
So
I mean, it was like I wasn't trying to memorize. It was pure theory. Like I was, I thought it would work.
Yeah. Yeah. So again, it's the key is to write it out, and then you'll see. Okay, so that's it. This is actually, the funny thing is, this might be the longest quiz ever in terms of number 4 different questions, but each question was really quick. So actually, I took a lot less time than the 20 minutes, and hopefully you did too, that you had no problem with time. But there's a lot of little details in this stuff, and that's going to be true today too. Today's a lot of details day. Any questions on that? Okay, I want to mention something because I got some emails about it. You have to be very careful when you're doing computer homework about format. Okay, I'm not picky on quizzes where I grade it, but when the computer grades it, it's picky about format. So if you're given vectors and you want to find, a vector from those vectors, you have to write it in vector format. So that means pointy brackets or IJKs. You can't use curly brackets on the computer to talk about vectors. Okay, so that's just a note for computer work, is that you have to pay attention to what they're asking and you want to use their style. Because I got a few emails saying it's not fair that I got taken off when I use parentheses instead of pointies. But you need to use the pointies for the computer. And one thing to remember is that you're always allowed to retry the problem. So if you didn't get it right because of your notation, then just redo it. And it'll be different numbers and stuff, but it'll always be a similar problem. Any questions on that? Okay, are there any questions about anything else? Because we're on Q&A time. Any questions? Okay, if there's no questions about anything else, then what I'm going to do is start talking about how to multiply vectors. Okay, and multiplication actually is a lot deeper than it sounds. So the first thing is there is no like really good way of multiplying vectors like you're used to multiplying numbers. So there's going to be a couple different definitions, and we're going to use those definitions, and this is true of just about all math. We use a definition because it's useful. If a definition is useless, there's no reason to use it. Okay. And what we're going to do is we're going to talk about one version of multiplication that's called the dot product. Okay. It has some issues in that it doesn't do what you're used to with multiplication. If you multiply two numbers, what do you get back?
A product.
But what do you get? You get a what?
A number.
You get a number, right? And it would be really nice to multiply two vectors and get a vector, don't you think?
Yeah, that would make sense.
Yeah, unfortunately, there is no way of doing that in general. Okay, there is no way of multiplying two vectors and getting a vector that works in general and that has any use in the real world. So that's a big note, is that it's a big issue with vectors, is multiplication doesn't do anything. There is no true definition of multiplication. So we have some kind of definitions of multiplication. So we'll still use the word product, but we won't use multiplication. We won't use the word times even. And the first is the dot product. And again, if you had pre-calc here, then you've seen this before. If you haven't, this could be your first time, but here's the big definition. Okay, let's suppose that V is the vector V1, V2, V3. And W is the vector W1, W2, W3. Okay, be vectors in R3. And I want to make a note. You could do this in R2 also, and it'll still work. Okay, you can say, let's say you have V as V1, V2, and W is W1, W2. Just kind of erase the 3 part. And I want to make a more general note. This works in R anything. So R100, you can still talk about the dot product. Okay, as you'll see that with the definition. We're going to say the dot product of V and W. So let me write that out. The dot product of V and W is V dot W. Do not say the word times because it is not times. V dot W is equal to V1 W1 plus V2 W2 plus V3 W3. What would happen if it was R2 and R3 instead of R3? What do you think would happen to this dot product? Any thoughts? What would the definition look like if we were in R2 instead of R3?
We would only have 2 terms, not the last term.
Exactly. You get rid of the V3 W3. You just get rid of that. What if you were an R100? Any thoughts?
I feel like there's a faster way.
Yeah, you certainly don't want to write 100 of them. There's no faster way to actually compute by hand, but to write out, just as a definition, use a sigma notation. So let me write that down just so that you get used to it, so that if you're an R something else, this is how you would do it. So this is, go. Uh-oh. Not showing my equation editor stuff. Let's try it this way. Okay, now it's showing. Okay, so this could be written as, in terms of the nicer way, as a summation from n, let's go I equals 1 to 3 of v sub I times w sub I. So if you're an R100, what's the only difference?
It would be 100 is I. Like
Not I equals 100, but you would, the 3 would become a 100.
Oh, okay.
So right, that 3 up here would be a 100.
Yeah, that
And that's
makes
the
sense.
fast way to write it. And by the way, if you do coding, and I strongly recommend learning how to code, if you ever want a good job in STEM, coding is important, okay? And it's not going away. Then you would do this as a for loop, and you would do for, say, int I equals 1, comma, or semicolon, depending on your language, and then 3, and then you would say vi wi, vi times wi. Okay, and then plus plus. So just note that coding is important in the real world. I don't test you on coding, but I will tell you it is the number one thing that you want to make sure you learn if you want to get a really good job. Okay, in any STEM field. Any questions on this big definition? Okay, doing it is easy. So let's take a look. I think did I write an example? I'm trying to, yeah. I think I'm gonna let you try because it's so easy. I bet you can all do it. So let's see if you can take the vector 4, -3, 1 and dot it with 2, 5, 6. Let's see if you can do that. I recommend doing it on paper. And then writing, and then you're, because there's some arithmetic to do and it's easy to make mistakes in arithmetic. So let's give you a minute. And it's very basic arithmetic if you understand the definition. Okay, good, good. So what we do is we do 4 times 2. And then plus, we do -3 times 5. And then plus, we do 1 times 6. And that's 8 minus 15, which is, so 8 minus 15 is -7, plus 6 is -1. That's all there is to it. Any questions on this dot product? Okay, there's issues, and this is why this is not multiplication. Could you do, say, u dot v dot w? What do you think? If I give you 3 vectors, can you dot them?
I would think so, but you just have to add a term.
Okay, one
To,
more
like-
guess. Can you multiply them? Can you dot them? No. Okay, so u dot v dot w actually makes no sense because u dot v is a number and numbers can't dot. Does that make sense? So you can't even talk about 3 of vectors dotted together because you can't do it. So that's a big problem, right? With multiplication, you want to be able to do that, right? X times Y times Z, of course you want to multiply 3 things. You can't do that with dot products. So there's a big issue with dot products, and that's the biggest issue, is that you don't get a vector when you take the dot product of 2 vectors. You get a number. And it gives you all kinds of problems. But we can still talk about properties. You just have to be careful. So you'll notice there is, in our set of properties that I have written here, there is no u.v.w. But what we do have is v.w equals w.v. Okay. What do you call that, by the way? What's the word in math? One word.
Is it fog?
Fog?
Wait, no, that's something different.
Definitely not fog. Associative. Good try. That's actually number 2. Sorry, actually, no, yeah, that's going to be for a different thing. It's not associative, but it's good try. Starts with a C. That's a hint. Composition. Good try. Not quite. Different one that starts with a C. Comparative. No. Commutative. Well, your spelling's interesting. Not communicative, but commutative. Okay, so it's called the commutative property. And that's no different than commutative property of addition, commutative property of multiplication. Well, you have the commutative property for the dot product. Okay, then we have u dot v plus w equals u dot v plus u dot w. What's that one called? See if you remember. This is basic math. This isn't, some calculus thing. Yeah, good. Distributive property. So we now know that the commutative property works, the distributive property works. Okay, then we have C, not dot. C, if I write C, what do you think C stands for? Hint is it's not a vector. Yeah, C is a constant. Okay, anytime you see C, that pretty much always means we're talking about a constant. So C times V dot W, notice they say times for the C, because it's a constant, it's not a dot, is equal to CV dot W, which is V dot CW. And that is kind of an associative property. But it's an associative property of a mix of scalar multiplication and dot product. Okay, and then we have number 4, V dot W equals the magnitude, V dot V, is equal to the magnitude of V squared. Okay, all these are important, by the way. What I'll do, and I'll let you choose which one. I'll prove one of them. Which one do you want to see? Pick 1 through 4.
3.
3 it is. Okay, I think I'll do it in R2 just because it's less typing. So, and I'm going to, just to make it a little easier, I'm going to let V equal, let's call it A comma B instead of V1, V2 because it's less typing. And W, I better not let it AB because the next letter is C and I can't use C. So how about, there's no good letters. I'll go AB. And W equal, how about R comma S? So then just do it. So proof of 3. Well, what is C times V dot W? I guess I got to do it in equation time. C times V dot W. Well, let's just do it. Equals C times. So you take the dot product. It's AR plus BS. Anyone lost on that? Just plug it in. Okay, and that's, you get a car, I guess. CAR plus CBS. Any questions on that? Well, now let's do the next one. And the idea is I better get the same thing. So let's do CV dotted with W. Well, that's CV, which is going to be CA comma CB dotted with W, which is RS. And that's CAR plus CBS. So I just proved the first equality, right? So now I just do the next one. I think I'll copy that one. Less typing. So V dot CW is equal to V, sorry, it's equal to AB dotted with, and then CW is going to be CR comma CS. And I do that dot product and I get ACR plus BCS. Are those the same thing?
Yes, because the terms are the same, just in different order.
Yeah, it's multiplication. Then these CAR, BS, those are all numbers. So we're just talking about multiplication, and we definitely know the commutative property works for multiplication. So we're done. That's it. That's the whole proof. It's kind of a boring proof. Sorry. Nothing like fancy. You just do them. But I think it's good to get used to doing them. Any questions about these properties? Okay. Any questions? Okay. Just notice, I'm not sure how many of you are taking the Math 202 class in the fall quarter, but this stuff is really important in the Math 202 class. What you're going to be doing in Math 202, instead of things like, the vector 3 comma 7, you're going to have f of x comma g of x. And you're going to have vector equations, and you're going to take derivatives of these things, and you look at things like what is the derivative of the dot product, where each vector is a vector function. Really cool stuff, really important. So I'm just giving you a heads up. We're not going to do that in this class because that's next class. But we are doing dot products, and this is what a dot product does. Any questions so far? Okay, now comes an interesting definition. I want to see if you could tell me, what does it mean if you have two vectors? What does it mean to say theta is the angle between those two vectors? What does that mean? Can you tell me what that means? I mean, you dealt with angles, for many years. Can you tell me what that means to say that the angle is pi over 3 between two vectors?
The space in the middle.
Okay, but what does space in the middle mean? What is okay? Now you can't use the word angle to define angle. You can't say the angle is the angular displacement because that's saying the angle is the angle. So you got to be careful about that. The space in the middle actually is a little tough because that could be area. It's tough. And what if it was in 5 dimensions? Can't draw a picture. Is that clear? So here's the issue, is you all thought up until today that you knew what angles were, but you really didn't. So today we'll actually have a formal definition of angle, which is undeniably works in any dimension. And here's how it works. So I call it a theorem / definition, depending on how you look at it. And that is, the first thing is V dot W is equal to the magnitude of V times the magnitude of W times the cosine of the angle between them. So in other words, oh, you know what? I forgot. Theta is the arc cosine of V dot W over at magnitude of V times the magnitude of W. And there's our definition of angle. And this is a solid definition. You give me two vectors, I can compute the angle for you. We know what cosines are. We know what arc cosines are. Those are formulas. And we know what dot products are. We know what magnitudes are. We know how to do arithmetic. So this tells us how to find an angle. Any questions on this big definition / theorem? Okay. So let's do an example. The examples aren't that hard. Find the angle between the vectors, let's call them V, equal 1, 3, 5, and W equal 2, 4, 1. And the idea is we know how to do it now. First thing is we can look at V dot W. Now, hopefully you can all tell me what V dot W is. What is it? Yeah, so it's going to be 1 times 2 is 2, plus 3 times 4 is 12, and that's 14, plus 5 times 1 is another 5, that's 19. So that's 19. Okay, notice V dot W is not a vector. It is a number. So V dot W is not 2, 12, 5. It's 2 plus 12 plus 5. So it's very, very important to get that down. Okay, now we get the magnitude of V. Now, hopefully you remember the formula for magnitude. That's the square root of 1 squared plus 3 squared plus 5 squared, which is 1 plus 9 is 10, plus 25 is 35. And then we have the magnitude of W. Same idea. That's going to be a square root. And we have 2 squared plus 4 squared plus 1 squared. That's 4 plus 16 is 20, plus 1 is 21. So we can say now that the angle theta is equal to the arc cosine of the fraction 19 over the square root of 35 times the square root of 21. Any questions on that? Okay, and by the way, I'm not even going to pretend like I know what the arc cosine of 19 over root 35 times root 21 is anywhere near, but we can use a calculator for that. Any questions at all on the angle between two vectors? Any questions? Okay, so this allows us to find an angle very much mathematically. Okay, I'm not talking about ruler and compass kind of stuff. I mean, literally, we have a definition, you plug in and you get an answer. Okay, any questions on that? Okay, now comes a really important definition. And that is that two vectors, v and w, are called orthogonal if v dot w equals 0. What's another word for orthogonal that you know from just life?
Perpendicular?
Yeah, perpendicular. Because notice if v dot w equals 0, that means the cosine of the angle is 0. The cosine of what angle is 0? Pi over 2. Okay. Cosine of 90 radians is not 0, by the way. But pi over 2, definitely. So the cosine of pi over 2 is definitely 0. So, and you're used to pi over 2 radian angles mean that you have a perpendicular line segments, I guess, or vectors in this case. But the formal word that mathematicians use is orthogonal. Don't ask me why they use two different words. I'm not the, don't shoot the messenger on this one. But we use orthogonal. So the awesome thing is it's very easy to decide whether angles are orthogonal or not. So for example, V and W that we just did, are those orthogonal? Yeah, definitely not. I took a dot product and I got 19. If you get 19, they're not orthogonal. Isn't that easy? Let me give you another example. Consider the triangle with vertices 1, comma, -2, comma, 3, 0, comma, 1, comma, 1, and 3, comma, 2, comma, 4. Is this a right triangle? All right, so you have some choices on this. What does it mean for an angle, for a triangle to be a right triangle?
The two of the vectors have to be orthogonal to one another.
Exactly. Two of the vectors have to be orthogonal, and then you get a right triangle. Okay. By the way, if you have a warm day with 90-degree temperature, doesn't mean you have an orthogonal, a right triangle, by the way. Just to let you know that.
Just a heads up, there was several homework problems that were in degrees on those last thing.
Yeah, so you know I didn't write them. I would never write a homework problem in degrees. So those were written by other people, unfortunately. Sorry about that. But in this class, in calculus, you really want to do radians. Degrees in this class will, on any exam or quiz I give, we're going to use radians, period. Okay. So the idea here is we want to see are any of the angles, right angles. So are any of the two adjacent vectors orthogonal? So let's do the adjacent vectors. So how about the vector from 1, -2, 3 to 0, 1, 1? And remember, you find the vector from one point to another by subtracting the coordinates. So 0 minus 1 is -1. And then 1 minus -2 is 3. And then 1 minus 3 is -2. Let's get the next one. How about the first point and the third point? 3 minus 1 is 2. 2 minus -2 is 4. 4 minus 3 is 1. And let's get the third one, which is second point and third point connected. So 3 minus 0 is 3. And 2 minus 1 is 1. And 4 minus 1 is 3. So let's give them some names. How about you? is the first one? How about V is the second? And how about W is the third? So now what I do? What's the next step?
Multiply and add.
Not multiply and add. I take the dot product. Maybe that's what you're thinking, but take the dot product is what we want to say, because that's what the first half is all about. So we take the dot product, U dot V. Is equal to, well, we have -2 plus 12 minus 2. What's the important thing about that number? Yeah, in particular, well, the important thing is it's not 0. It's definitely not equal to 0. Okay. And now let's take U dot W. And U dot W is equal to -3. And then plus 3. And then -6. And you can see that's not 0. And then finally, V dot W. And V dot W is equal to 6 plus 4 plus 3. And that one is also not 0. So what's the conclusion?
Not orthogonal.
Yeah, a triangle is not orthogonal, or a right triangle. Any questions? Any questions on this? Notice that, this sounds like a geometry problem. No pictures needed. You don't have to draw a picture to talk about whether a triangle is a right triangle. It's all numbers. Okay, and so this works in 20 dimensions. Exactly. If one of them, well, if one is 0, we don't call it an orthogonal triangle, we call it a right triangle. So if there's one, if one of the dot products gives you 0, then it's a right triangle. Does that make sense? Any questions at all on checking to see if vectors are orthogonal? Okay, let's move on to the next little piece. A lot of little topics today. So the next one, I'm just going to brush through it really fast. And that is, let's suppose we have 2 vectors. We have a V and we have a U. Then often what you want to do is you want to say, well, you can project V onto U by think of a light bulb way up here, and it'll be the shadow as a right angle. Any questions on that idea? And the formula is that the projection of V onto U, that's how we read this, is equal to U dot V over the magnitude of U. Any questions on this formula? Okay, where do you think this is used? Any thought? What job might you have as a STEM major? Where are you going to use this stuff?
Aerospace engineering.
Maybe. I'm not an aerospace engineer, but I'm not sure. But there's one I'm definitely sure of. Pattern recognition in AI, definitely. Okay. It's a little too sophisticated to even talk about. Let me give you another one that most of you are very familiar with, and some of you do too much of, and that is gaming. Online gaming, computer gaming. So here's the thing. How many dimensions is a computer screen? Hopefully you all know. 2. And in gaming, in modern gaming, how many dimensions do you want to portray? 3 plus time. Okay, but visually 3. So it turns out that what you're going to do is you're going to project a 3-dimensional vector onto the vector, which is the x-axis and the y-axis, basically, and that will give you how you want to show where that thing is. Okay, it's too complicated for me to go through it, but I want to let you know that it's a big application. It's a fun application. So if you want to do that, you think of having a view from above, but what you're going to see is 2-dimensional. And that's a projection also. Very similar idea, but kind of complex. Any questions on this big definition? Okay, the calculation is boring. So let's say let U equal, how about 1 comma 3 and V equal -4 comma 1. Then let's do the projection. So the projection onto U of V. Whoops. I didn't get a equation. There we go. Projection onto U of V is just equal to, well, it's a fraction. And U dot V is -4 plus 3, which is -1, over, you know what, I should add one more thing in here because officially it's times U. So it's -1 over the magnitude of U, which is 10, 1 squared plus 3 squared, square root of 10. Times 1 comma 3. Any questions on these calculations? Okay, so notice the projection's a vector, and the magnitude turns out is a whole, different issue, no problem. Any questions on that? Okay, then finally a little physics. And that is the work done by a constant force, F, from a point P to a point Q is the following. The work is equal to F dotted with PQ. Let me ask you something, because I have no idea, even though I wrote the course, believe it or not. Have you had this in physics yet? Those of you who are taking physics? Okay, so you have. So you've seen this before. I'm not going to spend a lot of time on it. It's really important, though. So if you want to find out how much energy is proportional to work, by the way, how much energy it takes to go like up Echo Summit, then this is what you do, where the force is, the force is kind of the combined force of gravity and friction, maybe some other things. And then PQ will be where you're going from one place to another. And this assumes that F is constant. So that's a big note, is that F is constant. If F is not constant, do you think it could be done? What do you think? Yes. Okay. But with Math 202. You need next quarter to be able to handle the non-constant work in a three-dimensional universe along a curve that's not even a straight path. Just let you know that. So this can be done, and that's next quarter. Okay, I think I'm gonna, because we only have so much time, I'm gonna let you read the book to see an example of this, but just take the dot product of the force and that. So I want to move on, and I want to get into cross products. So as I mentioned, the big issue with dot products is you take two vectors and you don't get a vector, you get a number. You'd rather get a vector. So if you happen to be in R3, then we can actually take two vectors and get a vector. So here's a big definition. Let V equal the vector V1, V2, V3, and W be the vector W1, W2, W3. Notice these are in R3. This does not work in R2. It does not work in R4. It only works in R3. It's special for 3 dimensions. Then V cross W, that's how we read this, cross, is the vector that is the determinant of the matrix I, J, K, V1, V2, V3, W1, W2, W3. Okay, and you all remember determinants from pre-calc, right? Maybe not, but it happened. So what you can do is for the I component, you kill the first row and first column, and then you take V2, W3 minus V3, W2. So it's V2, W3 minus V3, W2 times I. For the J component, it's negative because you alternate, and it's V1, W3 minus V3, W1, and multiply by -1, and you get V3, W1 minus V1, W3 times J. For the K component, you take V1, W2 minus V2, W1. So it's the diagonals. That's how determinants work, and that's times K. Any questions at all on the definition of the cross product? Any questions? Okay, so I'll tell you honestly, it's so much easier to remember if you can remember the matrix. It's really obvious how to write the matrix. Okay, and knowing how to find the determinant of matrix is something you need to do anyway, because that's going to come up in your future, whether you remember it or not. So I strongly recommend using this matrix way instead of jumping to this formula, which is really hard to remember. Whereas a matrix is IJK, you write the V vector as the first row, next row, and the W as the next row. It's just easy. Okay, so let's try one. Find, how about 2, 1, -1, cross. How about 1, 3, 4. Any questions on that? Unfortunately, I hate this, but the Google, for some reason, doesn't do matrices. Isn't that weird? I made this in a table, but I'm just going to do it the kind of messy way. So I'm going to go I, J, K, and now we're going to have 2, 1, -1, and then we're going to have 1, 3, 4. Any questions on writing down the matrix? Okay, then I find the determinant. So for the I component, you look at this little 2 by 2, and that's 1 times 4 minus a -1 times 3, which is 7. So let me write that out. 1 times 4 minus -1 times 3. I. and then minus the j component. And for the j component, it's 2 times 4 minus -1 times 1. J. And then plus for the k component, it's 2 times 3 minus 1 times 1. Okay. Now it's just basic arithmetic. 1 times 4 minus a -1 times 3 is 7i. And then 2 times 4 is 8, minus a -1 times 1 is 9, and it's a -9. Minus 9j. And then plus. And then 2 times 3 is 6. Minus 1 times 1, that makes it 5k. Any questions at all on finding the cross product of two vectors? Okay, the good news is this is a little like multiplication in that if you take two vectors and you cross them, you get a vector. That's a good thing, isn't it? But there's some bad news. So the bad news is this doesn't work. It doesn't have all the properties of multiplication. So let me show you the biggest issue, and that's number 1. So V cross W is negative W cross V. So you want multiplication to be a commutative, but it's not. In fact, we call this anti-commutative instead of commutative. It's like bad commutative. Okay, so again, you can't call this multiplication because multiplication needs to be commutative. Okay, but the good news is you can actually do the distributive property, and U cross V plus W is U cross V plus V cross W. Okay, you can also distribute a constant, C V cross W is CV cross W, which is also V cross CW. Also, if you take V cross 0, that's 0 cross V, and that's 0. I want to ask you something. This 0 right here, is that the 0 number or the 0 vector? Yeah, that's the 0 vector because cross products give you vectors, not numbers. Okay, so that's good because that like works with multiplication. If you multiply by 0, you should get 0. Okay, now comes an interesting one. And this is one that you're not used to, that is V cross V is 0 for any vector V. Okay, and that's why, again, we don't want to call this multiplication because if you square the number, you get 0, and that's bad. So don't even think about this as multiplication because it's not. Okay, and then finally, this is a nice one. You can mix dot products and cross products. So U dot V cross W is U cross V dotted with W. Any questions on any of these properties? Okay, I think I'm going to forgo the proof because we only got, a short amount of time. And if I proved it, we can't do anything else, and there's more to do. Okay, maybe I'll show you, not prove it, but kind of show you the V cross V equals 0, because that's the one that looks weird. But if you look at this over here, okay, if you use V cross V, that would be V2 V3 minus V3 V2, and that's 0. And V3 V1 minus V1 V3 is also 0. And V1 V2 minus V2 V1 is also 0. That's why that one works. That's the proof, just kind of reading it. Any questions on this cross product? Any questions? Okay, one thing that you might want to ask is, why do you care, right? If the cross product wasn't used for anything, if it was useless, then it wouldn't be in this class. So it must be useful, and it really is. So let me show you some reasons why you care. Okay, one is V cross W is equal to V in magnitude times W in magnitude times the sine of the angle between. That's the magnitude of V cross W. Okay, again, I don't have time to prove all these things, but it's useful. Do you think it's easier to find the angle using this formula? Because remember that the theta then would be the inverse sine of the magnitude of V cross W over the magnitude of V times the magnitude of W? Or do you think it's easier to use the dot product where we had theta is the arc cosine of V dot W times the magnitude of V times the magnitude of W? What do you think is easier?
Dot product.
Yeah, the dot product. And the reason they're identical except for whether you have cosine or sine, and that makes no difference, right? It's just as easy to find a cosine as a sine inverse. But dot product or cross product, well, dot products are a whole lot easier than cross products to do by hand. The other thing is that the cross product only works in three dimensions. The dot product works in any dimension. So as a general formula, you can't even use the cross product to define the angle. Any questions on that? Okay, but just note, why is it immediate from the theorem that V cross V is 0? Why is it immediate that V cross V is 0 from this theorem? Exactly. The angle between anything and itself is always 0, and the sine of 0 is 0. So that means V cross V has to be 0 in magnitude. And if it's 0 magnitude, it's a 0 vector. Any questions on that theorem? Okay, now comes an example, and it's really the most important type of example, not these numbers, but the idea. And that is find a unit vector orthogonal to both the vectors V equals 2, 1, negative 1, and W equals 1, 3, 2. How might we do that?
Is it with the matrix again?
There's going to be a matrix, but in particular, it's going to be with the cross product. Okay. All right. So if you have to leave, then note it is recorded. It's because we still have a little less than 10 minutes. So what we know is the following. We know that V, let's write this out this way, V dotted with V cross W, maybe I'll need parentheses, oops, V cross W. What is that? And the idea is that's the same thing. See, V dot U dot V cross W is U cross V dot W. So I can use that. Let me keep that property. I want to see the property as we've got it. So V dot V cross W is equal to V cross V dotted with W. What's V cross V? Zero. And 0 dot anything is 0. And also W dotted with V cross W is equal to W dotted with negative. So I can pull the negative outside. I'm always allowed to do with the constants. W cross V. But what's that? That's also 0 for the same reason that V dot V cross W is 0, is that if they're kind of next to each other, you can write that as W cross W dotted with V, and that's 0. So that tells you, by definition, V cross W is orthogonal to both V and W. Any questions on that idea, that kind of idea? So we just take the cross product. I, J, K, and then 2, 1, negative 1. And then 1, 3, 2. And let's work this out. So we're going to have I times 2 minus negative 3, or 5I. And then we'll have J, 4 minus 1 is 5. That's going to be minus 5J. And then we have K, 6 minus 1 is 5. So that's going to be plus 5K. Okay, we want the unit vector. How do you find the unit vector? We divide by the magnitude. And the first, I'm just going to divide by 5. You can always just divide by number and then divide by the magnitude. And that gives you I minus J plus K. And now we take the magnitude, which is root 3. So I'm going to write it this way because I'm running out of time. Over square root of 3. And there's a unit vector that's orthogonal to both of these vectors. Very important to note, if you want the orthogonal vector, you take the cross product. All right. Next theorem. The area of the parallelogram with adjacent sides V and W is the magnitude of V cross W. Okay, and if U, V, and W are adjacent edges of a parallelepiped, have you heard that word before? Do you know what that is?
Does it have to do something with water?
I mean, I guess, but not really. Nah, nothing to do with PI. Good try, though. It has to do with a parallelogram in 3 dimensions. So it's kind of like a rectangular solid or a cube. A cube is to a square as a parallelepiped is to a parallelogram. So it's a 3-dimensional parallelogram. It means you take 3 adjacent vectors, and then you make a parallelogram in 3 dimensions. Any questions on that idea? And the volume of the parallelepiped is given by U dot V cross W, which is the determinant of the matrix with rows U, V, W. Okay, any questions on that idea? Okay, I'm running out of time. So I think what I can do is I can show you a picture. Easiest way is show you a picture this way. There's parallelepiped. Lots of pictures. So it's kind of like a cube, but it's not right angles for all of them. Okay. So they're all parallelograms. Any questions on a parallelepiped? And the volume of a parallelepiped is the determinant of the matrix in absolute value, actually.
It kind of looks like the piping you see on some ceilings,
It could. It could, although piping's usually got some
like
kind of-
air vents.
Yeah, air vents, not piping, but air vents. Yeah. Okay, so that's a parallelepiped, really important for structural engineering. Okay, we're running out of time. So I want to give you one last definition, and you may have seen this in physics, and that is let F be the force applied to a vector V. And I like to think of take a wrench and rotate a screw. Okay, you've all probably done that before. And the torque is equal to the cross product of V and F. So it's kind of how much force you need to apply in a way to rotate that screw. Okay, so who knows how to read this letter here, this first letter?
Tau?
Tau. It's a Greek letter, and it's read tau, and that's what people tend to use for torque. Tau is equal to V cross F. So that is capital F. That is equal to another, another major application of physics. I'm not sure what 2 pi is. I'm not sure what you mean by that. Yeah, crystal structures, by the way, do present parallelepipeds. Not all, but some. Tau is 2 pi. No, tau is V cross F. Okay. Tau is V cross F, the period. Yeah, so don't get it confused with anything with pi in it. But it's really important in physics, in engineering, because torque is important, not just because you're going to use a wrench, but where else might you care about torque? Ever you need a balance, that could be. And in particular, in structural engineering, you want to be able to handle a certain amount of torque so you don't break something. Because if something is twisting, then you don't want it to break usually. And so you calculate the torque needed to actually do the braking. And you want to make sure that you create a structure that is strong enough so that torque doesn't make that happen. So very important, like tornadoes have torque because they spin. It's kind of like a tornado makes a screw turn and the house could get destroyed from a tornado because a tornado has torque. Does that make sense? Okay, it might be that there's another 2 pi you might want to call tau just for fun, but in our class, no. In our class, tau is V cross F. But we're out of time. So I'm going to stop my share and stop the recording.